Chapter 22, Section 2 gives you a lot more ways to calculate power and electric energy. But what you should realize, how did they get this? I mean, I'm giving these to you now so that when you try to solve some of these problems, you can just look for the equation that you want. Before we said that power was equal to current times voltage, but we know from Ohm's law that voltage is equal to current times the resistance. And so if you just multiply this out, you get I squared R. Right? That's how they get this one. And there's various other manipulations of the basic equations to give you these. So in college, they wouldn't give you all these. Right? They would just assume you could derive the equation that you needed from the basic principles. Example problem 3 on page 602. They give you the electric heater. Here's what we plugged into the wall. Here was the coil wrapped around the wire, and they want to know how much power is dissipated. In this case, this looks very similar to the previous problem that we did, except that they're giving you the resistance and the voltage. So if we want to know what the power is question mark, we need an equation for power that has resistance, voltage, and I don't think we're going to need time. So we would probably use this equation, right? Right? So P is equal to V squared over R. And these are really just plug and chug, right? So I don't think I can square 120 in my head, so we'll have to square 120. Divided by R. And you already gave me the answer?
Yes.
What is it?
1,440.
1,440. That's after you divided by 10?
Yes, sir.
Okay, great, thank you. And this is a power problem, so power is again in watts. So 1,440, we have another way of saying that. If these numbers get really big, and you might be familiar with this term, that would be 1.44 kilowatts. Typically, when your meter outside your house is reading in kilowatts.